Hey, everybody. Welcome to DCARI's 30th virtual fire investigative training session. Today we have Cameron Novak, who is returning for the third time. Today, Cameron is going to present on portable electric space heaters. If you've come to any of our or attended any of our DCARI sessions, you know that Cameron is the OG, the original presenter, where we started this back in April of 2020 with session number 1 and 2. And now he's presenting session number 30. So without any further ado, Cam, go ahead and take it over.
All right, thanks, Bill. Yeah, so today the goal is just kind of to go over what we're looking at and the operation of electric heaters, and we'll kind of throw in some baseboard heaters as a bonus at the end. But it's something that we obviously run across on scenes fairly regularly, and in my opinion and my experience tends to be blamed as a potential ignition source more often than it deserves. So hopefully we can kind of give everybody a little bit more knowledge on that, on how these work, the safety devices that are involved, and what we typically are looking for if they're potential ignition sources. So what I like to do first, though, is I think we have to address thermal protective devices that are used in appliances and in space heaters as well, because if we forget or overlook these devices, which are pretty much built into just about everything that we will deal with, except for one appliance, which we could talk about another day. If we forget to consider how a thermal protective device, which is designed to prevent a failure or a fire, how that device failed to prevent abnormal operation, we're kind of ignoring a really important piece of data. These thermal protective devices, and these devices are designed to not cause a fire. And so we have to, anytime we opine that something failed, determine how it failed to do what it was supposed to do in preventing that incident. So one of the things that I like to talk about first is our a bimetallic automatically resetting thermostat, or a thermal cutoff. And what's kind of interesting is you might see the same device used in different appliances and be referred to as the same, or referred to with different names. And really, it's a function of what is that device doing in that circuit. So most often where we see these bimetallic thermostats is, or let me take a step back, sorry. When it's referred to as a thermostat, that's usually the operating thermostat that helps regulate the temperature under normal operation. And if you hear something referred to as a thermal cutoff or a thermal cutout, that's usually the high limit, last ditch, oh crap safety device if the thermostat fails, or some other temperature regulating device. So with these bimetallic thermostats, the way these are set up is, and hopefully everybody knows what a bimetallic element is, but essentially it's two metals bonded together, and as they are heated, they will expand at different rates, which causes them to flex. So if you look in the X-ray image on the right, you see this dark disc on the left side of the image, and that's the bimetallic element. So what that will do is, once it hits a certain temperature set point, it will flex. You can see it's flexed to the right at the moment. And when it hits a certain temperature, it'll flex to the left. And what that does is then pushes a ceramic pin to the right, which separates the two contacts at the bottom of the thermostat, or I guess on the right side in the X-ray here. So, and then once it cools off to a certain temperature, that bimetallic disc snaps back to the left, allows the contacts to close, re-energizes the circuit, allows it to continue operating. So that's how these bimetallic thermostats work. or resettable. You can also see this would be an example of a TCO in a space heater. So different style, same as concept of operation. It's got a bimetallic element, and as you can see here, the contacts are closed. There's the temperature rating and the manufacturer information. And so you can see in these images here, the one on the left, the contacts are closed. The one on the right, the contacts are open. And then here's just a zoomed in version of those. So all that's doing is opening and closing when it hits a certain temperature. And within this instance, the TCOs have a higher temperature set point than the thermostat, because we don't want it to be running on the high limit. We want that to be a last ditch safety device, so that we have repetitive or redundant safeties in these space heaters or any sort of appliance for that matter. Okay. So here's an example. I found this on the internet. It was kind of neat. Just an example of a snap disc thermostat, bimetallic. So you can see the contacts on the left, and then you can see the snap disc or the bimetallic disc on the right. So you can see how it flexes back and forth. So just an example of how these are functioning. So we also have variable bimetal thermostats, and where these are going to be most frequently used are space heaters, clothes irons. Those are probably the two predominant ones that come to mind right off the bat. But the way these work is as you turn that shaft, that's going to change the distance that the bimetal arm, which is the piece, the strip furthest to the left in this image that has that gray pin at the top. That's the bimetallic element. And so what that's going to do is as that heats up, it's going to flex to the right, and it's going to push those contacts apart. And so by changing the thermostat or that shaft position, we're changing how far does that bimetallic arm have to flex to open the contacts and shut off the electricity to that circuit. Okay. Oftentimes what you will see is, or the way we kind of refer to things is, when we refer to a variable bimetal thermostat, we'll see you've got what's called the stop right here. And then there's this little key or wedge that's attached to the shaft. Whoops, sorry. And so here we've got it fully counterclockwise against the stop. And then you can see in this image, the contacts are open. So this would be when we refer to these in our reports, we kind of reference everything back to its distance or proximity to the stop, the shaft in relation to the stop, its position to the stop. So again, fully counterclockwise against the stop is typically either off or in the low position. It's manufacturer dependent. So some manufacturers, the thermostats in this position, this fully counterclockwise, the contacts will be open. Other times they're just low. So don't assume that it's one or the other just because you find the shaft in that position. It's something we have to look at and make sure. So here's another example of just how that bimetallic arm is, the direction it's going to move and how it's going to push those contacts apart. So again, the higher, quote unquote, higher the setting on your thermostat, the more those contacts are going to move away from the bimetallic strip, and therefore the further it is going to have to deflect in order to open up those contacts. Okay. So here's a fully clockwise against the stop. So this would be consistent with the high position. And as you can see, the contacts are closed. And if you remember from a couple slides ago, you can see that the contacts are actually slid a little bit to the right. And there's actually a gap between this pin and this top moving contact. So that is how we're changing the temperature of a device, was we're changing how long that circuit is energized due to how long it takes that bimetallic strip to deflect. Okay, so just a kind of a blown up view of that. Right, so here's a thermostat, the shaft's in the fully clockwise position against the stop. Here's another example, kind of moving them back and forth. So you can kind of see it's a little hard because the whole thermostat assembly moves, but you can see that the contacts are moving away from that bimetallic element. And here's another animation showing it all put together. So all that's happening is we're changing the distance that the bimetallic element, excuse me, has to shift or deflect to the right in order to push those two contacts apart. So there's a hole in this contact arm that allows that pin to poke through. So the thermostat shaft moves the bottom or the contact on the left, and the bimetallic strip moves the contact on the right. Okay, so kind of a rhetorical question for those of you since we're recording this, but think about how does something like this, how do these devices vary the temperature of something such as a space heater? And the answer is it doesn't, right? It's not changing the temperature. It's not allowing a space heater to get hotter. The way it's, the heater is either on or it's not. What this is actually doing is changing the duty cycle or the time that the heating elements are energized and the time they're not. So on the low setting, I'm just going to pick some random numbers, but on the low setting, the heating elements might only be energized for 10 seconds and off for 30. Versus on the high setting, it might be the opposite. The heating elements are energized for 30 seconds and off for 10. We're just changing the time that those heating elements are energized, and therefore how long are they producing heat. We're not actually changing the temperature. We're not changing the resistance of the circuit. You could argue it goes from no resistance to an infinite resistance, but that's a little too complicated. So what we're really doing is just opening and closing a switch and shutting the heating elements on and off. Okay. Now, we'll get into non-resettable thermal cutouts or cutoffs. And this is say a 10-cent device that is in everybody's coffee maker. And if this thing bites the dust, your 10-cent device is now taking out your $30 or more coffee maker. But the way these are set up is they have a thermal pellet inside that goes from a solid to a gas when it hits a certain temperature. So what that pellet is doing is compressing these springs against the pin here. So if we look at this dark gray shaded area is our actual energized current path. We have current coming up through this pin. It makes contact with this star contact or a star washer. That then comes in contact with the outer casing, and then we have a complete circuit out the other end of the TCO. When that pellet sublimates, and when it hits that set temperature, it sublimates, it goes to a gas, the springs release, they're no longer compressed, and this bottom spring pushes that star contact away from the pin, and now we only have this one lead energized, and we've opened our circuit. Okay. So here's kind of a cutaway view of one. We'll have the pin coming in here. Here's this star contact, the two compressed springs, and then there's the thermal pellet. And that's the current path. And there's one disassembled, just showing here's that star contact. Here's the pin it's making contact with, little washers or spacers, and then your thermal pellet's still inside the casing here. So here's some examples, what a CT scan of one of these looks like. Here's one intact. Here's one that is open. So there's the pin. Here's the star contact. This is something we would see in a lab, but in the field at best, we're probably dealing with an x-ray. So in this case, you can see this one is open. Here's the pin. Here's the contact. Our thermal pellet's gone. The springs are relaxed. Here you can see this one is intact and the thermal pellet's still in place. Okay. So some other types of thermal protection. These are also bimetallic type devices. So the one on the left is a manually resettable bimetallic switch. So you have to press this little button on the back of it if it were to trip. The reason why we have those is, when something like this, just like our circuit breakers, when our circuit breakers trip, they're telling us there's a problem in the system. And so we don't want, there are certain instances where we don't want an automatically resetting device, because then it would never clue us in to some sort of abnormal operation of the device. So where I tend to see these most frequently, these manual resettable switches, is they're like flame rollout switches on a furnace, or a downdraft prevention on a wall furnace. So you want to have, you don't want those exhaust gases coming back into the structure, so it's used to detect that. These on the right here are bimetallic automatically resetting switches, and where I typically see those most frequently is in recessed can lighting that is rated for contact with insulation, or IC rated. I think these are used in some bathroom exhaust fans for thermal protection as well. But where I see these most frequently is, like I said, recessed lighting. So all of these things are things we want to consider when we're talking about any sort of appliance. And specifically, we'll talk about space heaters today, or portable electric heaters. So hopefully everybody knows what the ignition handbook is and knows where to maybe get a copy or get access to it. It's no longer in print. You can find some old print copies online. You can also purchase a PDF of the document, which might be easier because you could search it a little bit easier that way. But the ignition handbook talks about portable heaters, and essentially they come in two separate varieties. So you've got radiant and convective heaters. What we typically refer to is something that has a visible glowing element, or I'll kind of throw the caveat that it might have, under some conditions or circumstances, a glowing element would be a radiant heater. And then pretty much everything else is a convective heater. So convective heaters typically are the oil-filled heaters, or your baseboard heater. They rely on the natural convection of the heated air to distribute that heat throughout the space, versus a radiant heater is going to have a glowing element. So here's an example of a convective heater. Typical controls in these: this one's got a 4-way switch. It's also got a variable bimetallic thermostat right here. It's just below that power switch in this photo. You've got a little indicator light here to show you it's on or not. And then down here, we've got the heating element and a high limit switch, or a bimetallic TCO. So that's our high limit. Okay. For these types of heaters, they're typically pretty benign as an ignition source, unless there's some sort of failure of the controls. They're, I don't want to say that they're essentially designed for you to hold your hand on them all day, because it would hurt. It's going to be uncomfortable, but the temperatures that they're designed to run at are pretty well below the ignition temperature of most common combustibles. As you can see here, the ignition handbook talks about they're maybe a fifth, as far as at fault for a fifth of the number of fires as a radiant heater. And then when they do fail or cause a fire, it's usually a malfunction of the wiring or the controls. So this is just an example of one that we had tested at the FRL a few years back. The numbers indicate which fins you'll see in the next graph. And then the red dots are the locations that we placed thermocouples. So it shouldn't come as a surprise that, seeing as how the heating element is down here in the bottom, these temperatures should be the hottest temperatures we see across the whole thing. And lo and behold, that's pretty much what we see. So highest temperatures that we got on these were just over 268 degrees, but less than 300. So, again, not something that is going to be a real great ignition source in any sort of reasonable amount of time. I ran a test a few years back on a brand new one of these heaters, and I took brand new cheesecloth and I actually, let's go back a slide, wrapped it around the whatever you want to call it, around where the space heater was contained, and tied a knot in it and left it for an entire 8-hour day. And that cheesecloth went from white to barely off white after 8 hours. So it's not something that's going to burst into flame in any, I guess, reasonable amount of time is the way I would call it. And if it does burst into flame, my guess is it would smoke like crazy long before it ever caught flame. In this instance, you're talking about, you would have to basically bring that fuel up to its auto ignition temperature, because there really is no form of piloted ignition source in this area unless the heater fails. So again, pretty benign ignition source in the grand scheme of things. So radiant space heaters. So the ignition handbook talks about how these may or can produce heat fluxes of around 10 kilowatts per meter squared at the grill. And if you recall from your fire dynamics, you'll know that as I move away from a heat source, my heat flux that I'm going to receive is going to drop off with the square of the distance. So if I double the distance from my heat source, I actually drop the heat flux that I receive by a factor of 4, or to 1/4 of what it originally was. So again, kind of like with the convective space heaters, unless there's some sort of failure that results in like an arc or a spark, there's really no piloted source of ignition. So you have to consider what the critical heat flux for ignition and what the auto ignition temperature of that fuel is, and whether or not that fuel can auto ignite at a heat flux of less 10 kilowatts per meter squared or less. Most fabric and paper goods, as you can see here, require significantly higher heat fluxes than 10 kilowatts. Cardboard, per the ignition handbook, can be ignited at below 10 kilowatts. I think from what I recall, it was 8 kilowatts per meter squared in the ignition handbook. Now, I will just kind of throw the caveat in there that I think that reference, as far as that 8 kilowatts per meter squared, I forget the time frame on that, but that might have been back in the 80s or 90s. So does that change things as far as, are things made differently today or not? That could obviously change the ignition properties of those fuels, but we won't dig too far into that. But again, this is at the face of the heater, so pushing something up against the grill of the heater, which is obviously a gross misuse of that device. If you've ever read the instruction manual for any type of electric heater, they pretty much all say keep everything that could burn 3 feet away from the heater. And what I'll show you here soon in a few slides is that's quite a significant, quite a bit of wiggle room on the manufacturer's parts, which is not a bad thing. But again, if we're going to push something up against the face of a heater, we have to consider A, its misuse, but B, how does the thermal protective device or devices that are built into that heater, how did they fail to prevent ignition of that fuel? Okay. So this is one that a type of space heater we see pretty regularly, uh, and so depending on where you're at, I think here in the Midwest we often refer to them as milk house heaters, but this one's got it's got a four-way switch, so high, low, fan only, and off. We've got a power indicator, and then our variable bimetal thermostat. On the inside, we've got here's our four-way switch. It's got the variable bimetal thermostat. It's also got a tip switch on it or an anti-tip, however you want to refer to it. So if this thing were to tip over forwards or backwards beyond, say, 30 or 45 degrees, this pendulum is going to open these contacts. Okay, so here's kind of showing how that works. You've got the little pendulum, the weight here that will swing forwards and backwards. Thing to remember is this does not work if it falls to either side, only forwards and backwards. So there it's tipped forwards. You can see that this face pushes against the contacts and separates those. And here you can see pushing it forwards, pushing it backwards, consistent with falling forwards or backwards. Some other types of tip switches, which I think would be my preference as far as use in appliances. This one's got a little plunger that sticks out the bottom of this space heater. This is the inside of it, so this plunger pushes on this lever. Doesn't matter which direction the heater tips, that plunger will, the spring will pop the switch open, and it doesn't matter, again, forwards, backwards, or either side. Another example of a tip switch, this one actually has like a little ball bearing in this dome. And so as long as this heater is vertical, that ball bearing presses down on the switch right here and keeps the circuit closed. If you tip this heater any direction beyond about 30 to 45 degrees, that ball bearing falls out of that little detent in the bottom, opens the set of contacts, de-energizes the circuit. So, this style and this style tend to be, I would say, more all-encompassing, more safe in that it captures any direction that this heater could go. Right. So one of the things we might want to look at is what is the position of the thermostat. So looking at it from the outside of the heater, you should be able to see something like this. Maybe it's fully counter or fully clockwise against the stop. That should be pretty obvious here. Um, Knowing whether it's on or not or not, or what temperature setting it might be, could be important in our analysis. One thing that's important to look at, we do often try to see, did that bimetallic element activate? And obviously in this position, this condition, it's deflected in the opposite direction that we discussed earlier. And what I found is over time, the more I've seen of these, any one of these that's been through a fairly significant fire and received a lot of heat, when it cools off, it kind of overcompensates and goes in the opposite direction. So seeing one deflected in this position is not uncommon, especially if it's been in a fairly significant fire. I took one and just put a propane torch flame to it, and when it cooled off, it did that, and it wasn't all that long of an exposure. So something that we see fairly frequently. Typical heating elements in these, something we're going to want to look at. Was there a failure of the heating elements? Is there some sort of fuel that was introduced and is still remaining next to the heating elements? Okay. So here's just some rough temperatures based off of steady state operation. So about 187 degrees Fahrenheit at the grill and 345-ish at the heating elements themselves. If you block the front and rear grills, shouldn't come as any surprise. You're trapping all that heat, and the temperatures are going to be a little bit hotter. But nothing too awful crazy there. And so here's just a little bit zoomed in on the heating elements. Typical connections on these, a lot of crimp connections are used, which the connection between the crimp or at the crimp between the wire and the connector, that could be a potential failure point. There has been documented instances of crimp connections that have failed in the past and led to high resistance connections. But usually, in something like this, how does a failure here translate to a fire outside of a metal box? Probably pretty unlikely. It might lead to a little smoke, some heating of the wire insulation, but it's generally not going to cause a fire outside of the box. That might be a different story if we're talking about a heater that has a plastic enclosure. Okay. So here's an example of heating elements when they're glowing. And I would pose this question to you for anybody that happens to have one of these or has used one or seen one in operation. Is this normal? Is the glowing heating element normal conditions for this type of heater? The answer is no. Guess why? That fan is keeping those heating elements just cool enough that they're not glowing under normal circumstances. So is the fan potentially a form of thermal protection? Absolutely. It's providing convective cooling and keeping those heating elements from glowing under normal circumstances. So here's just an example showing what happens between two heaters. They're completely identical other than one of them has the fan taken out. You can see as time goes on, 4 minutes, the heater without the fan is significantly warmer. But then what happens? The thermal protection device, the TCO kicks off. And now there's no longer heat being produced by the heating elements. And in this instance, it takes more than 25 minutes, as you can see here, before that TCO resets itself and re-energizes the circuit. So another factor to consider is if you trip that thermal protective device, you may have an extended period of time before that resets itself and cools off to the point of restarting that device. Okay. So the 4-position switch, and these are pretty common between different types and brands of heaters and styles. But you can see the way these are set up, you've got power coming in the lower left, the high heating element lead coming out of the top left, the fan lead coming out of the top right, and then the main heating element in the bottom right. And so fan only, when you do the first quarter turn, we energize the fan only. So here's power coming in, here's the contact for the fan. You can see the high heating element and the main heating element are still de-energized. Another quarter turn, we've energized the fan and the main heating element. And then on a high heat, we've got all 4 contacts are energized. All 4 leads are energized. So here's kind of a neat animation just showing no matter what, the fan is always going to be energized unless it's off. In any position but off, the fan is energized. And every quarter turn essentially energizes one more contact or one more wire coming out of that switch. Okay. So here's your opportunity to play, engineer or not destroy. That's a bad way to describe it. Here's your chance to open up and perform a forensic examination on one of these heaters. So, kind of think to yourself, what do you see? What observations can you make from this type of heater? And I'll kind of walk through mine. Obviously, this thing has significant amount of fire damage. It's oxidized. It had been through a fire. It's been whacked. If we look at the back, similar amount of oxidation. One thing you'll notice is we are missing most of the power cord. If we zoom in on the back here, we'll notice that there is a nice little bite taken out of that conductor entry point. So if this is a steel enclosure, what would cause that little bite to appear in the steel? If you're saying it's an arcing event, you're spot on, right? So we've got an arcing event, so therefore we can opine that the heater was most likely plugged in at the time of the fire. Right? We're going to look at the fan. Obviously, the fan motor is present. The fan blades usually are aluminum, so they melt out pretty easily. But I will tell you that the motor windings, where we can see them, they all look intact. So we could probably rule out a fan failure. We'll look at the inside. Now let's take stock of what components we have. So we've got our four-way switch. Here are some of our leads going to that switch. Here's the thermostat. Here's the pendulum or the weight for the tip switch. I will tell you that the connections are all intact. There's no evidence of high resistance connections. The heating elements are intact. This junk right here is just the melted aluminum from the heating element. Here's our TCO. That's open and deflected, which is good. We don't want that to be welded shut. Here's the weight. Here's the thermostat. So we know it's deflected. It's deflected away from the contacts. I'll tell you that the contacts are open. Excuse me, pardon the cursor. Take a look at the x-ray. What position do you think the four-way switch is in? Leave it up for a second. Okay, we'll come back to that. All right. So 921 talks about you don't want to eliminate an ignition source just because there's no obvious evidence of a failure. So, and as a perfect example that ties into our current discussion, just because this electric heater doesn't have any arcing on the wires or the contacts aren't welded shut, there might be other ways in which it could cause a fire that maybe don't involve an actual failure. So do we have something that combustibles were stored too close, or something in combustibles were inserted inside of it? Those are things we might have to consider. Okay, so kind of wrapping up all our observations, we know that we don't have the entire power cord. We've got significant fire impingement damage to it. We know we have arc melting at the conductor entry point. We have all of the components and debris in there consistent with what we would expect to see. The fan motor is intact. All our connections are intact. The heating elements are intact. The TCO is present. It's deflected open. The contacts aren't stuck. We have the tip switch, or the anti-tip switch is there. The thermostat contacts are there. They're open. The bimetallic element is deflected. We can't, in this instance, particularly say what position the thermostat was in because the shaft was melted off. And we can say that the four-way switch was probably on, and probably on high. If you go back and look, looks like we've got all four contacts are energized. Okay. So the conclusions, the heater's probably energized. It's probably on high. We have all of our thermal protective devices there. They're in a position or condition consistent with functioning and operating normally. So there's no evidence of any sort of malfunction or evidence of an electrical failure. The only thing we can't really rule out is, was there maybe a pinched cord failure of the power cord, or maybe somebody inserted something into the heater to ignite it that way. Okay, so here's an example. Again, x-rays are our friends. If you can find a bomb tech or make friends with somebody who has an x-ray. A few of us at ATF, a few of us electrical engineers at ATF travel with a portable x-ray. So if you need that assistance, we can provide that service. But here's an exemplar heater. Again, slightly different style. We've got the bimetallic thermostat here. This one has just a rocker switch to pick high or low. And in this instance, instead of being on this side, the TCO is up here. So this is it right here. So again, having an exemplar is really handy because we can kind of compare what we think it should look like with what we're actually seeing. So here's an example from a class where we allowed the students to manipulate these heaters. One thing I like to do is follow my conductors in and see where they're going. And one thing you'll notice pretty quick is, hey, why are the leads for the TCO cut and kind of hanging out here in the open? That's a problem. Here's another example. In this case, they've basically bypassed. We've got one wire going all the way up to this heating element. So we're going to zigzag through the heating elements. And here's the other wire, bypasses the thermostat and that power switch altogether and the TCO. You'll also notice there's no fan motor here. So they took out all the thermal protected devices plus the fan to make this ignite some fuels. And I don't know what this group was thinking. They just took everything out, but I don't know, kind of fun to look at nonetheless. Obviously, this is a problem. So this was a fire that I got involved with, not so much the scene exam, but I was tasked with looking at some photos and looking at the heaters themselves and asked to do some testing. And the way this scenario was described to me and captured in photographs was we had two of these quartz infrared heaters. They were side by side with one of them on top of a cinder block. And they were both pointed at the plastic tank for a water softener where you would have the salt pellets and the water. And the only thing that burned in this room was that brine tank. So the question was, would these two heaters spaced about 2 feet from the brine tank, would they cause a failure or melting or burning of that brine tank? So I never pass up an opportunity to test and characterize a space heater. So we did that. And first we took each one of these separately. And then we did a test with both of them. And we kind of did a worst case scenario. Rather than having the one on the cinder block, we put them both side by side to make it worst case. This would at most be the worst exposure that brine tank would get. And so what you see here is the heater on a sliding track. We've got 6 heat flux gauges with thermocouples right next to the heat flux gauges. And then we gridded out the grill on this. So the heat fluxes with right at the grill surface, the highest we got was just over 8 kilowatts per meter squared. So we have the potential, per the ignition handbook, to ignite cardboard. When we moved that heater 12 inches away or a foot away from the heat flux gauges and the instrumentation, we dropped down to 1 kilowatt per meter squared. And then when we moved it to 2 feet away, which was the distance that we were dealing with in our actual fire scene, we're about 0.5 kilowatt per meter squared. Here are the temperatures that were measured during that same test. So at the grill, we're just shy of 172 degrees Fahrenheit. Now you have to remember the temperatures might be a little bit higher in the real world if we had a actual surface there to absorb that heat, but this is the temperature captured by the thermocouple bead. So, take that for what it is. It might be a little bit different. But this is where I think the heat flux becomes a greater indicator of the propensity for ignition as opposed to the temperature. So here's the other space heater. They were 2 different brands, but same styles or same design. Again, just over 8 kilowatts per meter squared. At the grill, we're around 1 at a foot away and 0.5 kilowatt per meter squared at 2 feet away. So, and then there's the temperatures, roughly similar temperatures. So one thing that I want you to ponder is if both heaters were putting out half a kilowatt per meter squared, and I were to put them side by side and cant them so that, or focus them so there is a focal point at 2 feet away, what do you think the combined heat flux was at that 2 foot mark? If you guessed 1 kilowatt per meter squared, you'd be right. So we have half a kilowatt plus half a kilowatt. Now think back again to fire dynamics. What is 1 kilowatt per meter squared representative of or consistent with as far as the heat flux is concerned? We know that 20 kilowatts per meter squared at the floor is what we would see at the onset of flashover. What is 1 kilowatt per meter squared consistent with?
The sun.
Thank you. Yeah, so standing outside on a sunny day getting a sunburn. So at best, that brine tank was getting a sunburn from these two heaters. There was no way that it was going to ignite from 2 feet away from these heaters, which didn't have any sort of failure associated with them. Okay, so this was something that was the result of a class that I taught earlier this year. I was down in Florida. The organizers bought a brand new heater like this, and I was, in all of my travels and the testing I've done, I've had a real hard time igniting things with appliances that haven't been manipulated. And so I had the class. I told them, don't do anything, don't bypass anything, don't shove anything inside the heater. Just try and set fire to it. Kind of, think of what a typical person would do. And so they put a towel and draped it over this front bar of the heater. And I was at first said, yeah, there's no way it's going to happen. I don't know how well it'll work. And 10 minutes later, the towel is on fire. And we repeated that and got the same results. And I got a little concerned that I started digging into the heater, and okay, I located where the TCO was, and the thermostat was in the top. You can't see it, but in the top face here. And the thermostat was just above the heating elements behind a reflective shield. And I was worried that maybe this was a poor design. So I emailed a contact at CPSC, the Consumer Product Safety Commission, and I said, hey, here's some photos. Here's the heater style. It was brand new. Is this a bad design? Does this pass the UL test? And they ran some tests, and these are the photos they gave me, and it does. So the UL test is you have to put a terry cloth towel over the heater, drape it over the heater, and it can ignite. And you can see the cloth, the towel is definitely discoloring here. But this is what we ran into in our class. So what's the difference? It's the ability of that towel to trap the heat and transfer that heat to the thermal cutoff and open it up. So it passes the UL test, but it doesn't pass what I would call the real world test. I think that this could be a potential issue that we're dealing with. But I think in the grand scheme of things, these quartz infrared heaters, if you're going to blame a heater as a potential ignition source, it probably needs to be something like this. These are probably our most likely candidates for ignition, or at a minimum, something that has a glowing heating element. Okay. I'm going to skip some of this video, but I wanted to show you some of the demonstrations at the end. Bill, if you're still there, let me know if the audio doesn't come through. Oops.
This morning,
Skip to the end.
tips. One, people need to realize that these are small.
Sounds
but they
good.
draw a lot of electricity, so
Okay.
one, you plug it directly into the wall.
And that's a big tip. Plug the heater directly into the wall. He says some people use cheap extension cords to move the heater closer, but many extension cords can't handle that amount of electricity. Just watch when he does it.
There you have it.
So obviously this is not the heater plugged into the extension cord. This is something else, but this is a poor connection, and he's not overloading the cord. That that's, this is probably a cord rated for that, but this had a prior high resistance connection. And they just showed that as a potential issue. One thing kind of to talk about overloading the cords, a typical 1500 watt space heater will pull about 12.5 amps of current. And most of these cheapo zip cords, such as this one that they're showing here, are probably only rated for about 8 to 10 amps of current. So you plug a space heater in and you're already overloading that. Doesn't mean it's going to burst into flames immediately, because there's usually quite a bit of wiggle room built into those, but it is something to be aware of. Okay, so let me stop it here.
What's the next tip? The next tip is we keep this 3 feet from anything combustible that will burn. The couch, the end table, anything that will burn. Best to do it in the center of the room.
And you were telling me, as ridiculous as it sounds, people sometimes let blankets fall right on top of the heater like this.
That's correct. And this heater's hot enough that it can catch it on fire. And then next thing, the room's on fire and then the house is on the ground.
To show us, Jamie sets up a real-life demonstration inside this real house, which is already being prepared for demolition. We have a team of firefighters standing by.
All right, heater on, blanket on. And we'll see what happens.
Remember, this happens in homes all the time in just several minutes.
There we go. We have ignition.
And you see how fast these fires can spread because the blanket's on fire.
Okay, so I'll stop it there. So a few things that I want to kind of throw out there. Mr. Rawson kind of reports this as several minutes, but this was actually like a 15 or 20 minute window from when they turned that heater on and placed the blanket to when ignition actually occurred. And it also smoked quite a bit and would have set off a smoke alarm long before it actually ignited. So that was my dad, who did the demo for him. And he had tried to, he had asked to put smoke alarms in to kind of show, hey, these would go off long before ignition, but they didn't want to make it a smoke alarm piece. They wanted it a space heater safety piece. So that is kind of a piece of the equation that's missing. But, again, if you look at the placement of that blanket, that blanket isn't covering the whole face of the heater. So they're striking a very fine balance of trapping enough heat to ignite the blanket while also dissipating enough heat to not trip the thermal protective device. I had this same style of heater in our lab once. I took a stack of newspapers, covered up the whole face of it, and within 30 seconds, the TCO opened up and shut the heater off. And I know they've done this. They've attempted to take that same heater out at the National Fire Academy, and they tried to replicate this, and they were not able to. So I don't know if they just, if my dad was that good at striking the balance on that heat transfer, heat entrapment, or if they manipulated or bypassed the safety device on these, I don't know. But apparently at the Fire Academy, they've had some pretty poor luck. It's something I'd probably like to try myself someday and see if we could replicate this, but haven't had the time to do it yet. Okay. So kind of wrapping this up, think about when you come across a space heater, what needs to fail for one of these to cause a fire, and does it actually have to fail to cause a fire? There might be circumstances where nothing fails and you've got materials introduced or pushed up against it that now are able to auto ignite. But again, that heat flux is a key factor in the equation. And unless something's up against the grill, it's probably a pretty benign ignition source in that sense. Okay. So again, we're going to have to look for evidence of overheating. Did our thermostat contacts get welded shut or stuck? Did the TCO contacts get stuck? Is there debris inside consistent with the introduction of fuels? Does there debris in contact with the heating elements consistent with the introduction of fuels? Did the tip switch somehow fail? Again, if we're going to say something ignited, what distance was that fuel from the face of the heater? So this is actually the photo from Florida where we did that demo with that heater. So you can see where we already ignited it once. This was the second time where I was paying a little more attention to capture some photos myself. Okay, so we're gonna kind of a little bonus material. I don't think anybody's gonna mind. We'll go over some baseboard heaters. It's pretty quick. So this is the typical construction of a baseboard heater. We've got a stainless steel heating element with usually aluminum fins around it to help aid in heat transfer. You've got your wiring coming in, and then a capillary tube up at the top, which is your primary thermal protective device. Okay, so here's an example of the fins and the heating element construction. So the nichrome heating element wire itself on the inside is surrounded by a magnesium oxide powder, which is a good insulator of electricity, but a good conductor of heat. And that allows the heat to get out to that grounded metal tube, and then the fins to help not only aid in convective heat transfer, but also prevent fuels from coming in contact with the hottest part, which is this tube down the middle. Okay. Thermal protection is provided by that capillary tube, so it contains a gas that when it heats, it expands, and that's going to press against a diaphragm and open up a set of contacts. The reason why we have a capillary tube is if I were to just have a single thermal cutoff, that only measures the temperature at a particular point. So if I've got a 4-foot long baseboard heater and my TCO is right here, and I have a failure down on this end, it's not going to pick that up. Versus the capillary tube's able to detect increased heat along the entire length of that heating element. Okay, I'm going to skip that. So examples, here's one we had done some testing on at the lab. So you can see we've got at the capillary tube here, at the capillary tube over here, here's a fin. Here's another thermocouple, excuse me, had a brain fart there. Thermocouple attached to the fin, and then another TCO right here at the top, the center of the top and bottom. So as you can see, the fins are going to have the highest temperatures. No surprise there. Upwards of around 280, 300 degrees. So fairly significant temperatures, but still for the most part below the auto ignition temperature of a lot of fuels. We kind of ran some, the guys at the lab ran some permutations on this test and blocked the top vent. And you can see that it cycles fairly frequently because it's not dissipating that heat. Here's another example of one where we they blocked, the guys at the lab blocked the bottom vent. So again, it just sat there and cycled repeatedly. And while we had some slightly higher temps, we're not maintaining them for any real length of time because they're just cycling. And slowly you can actually see kind of trailing off ever so slightly. Okay, so then they ran one test with some fuel in contact with those fins, just a piece of cheesecloth. You can see, temperatures are pretty consistent with the other tests, nothing all that crazy. Show you the video, and I'm going to kind of zoom through it. This will be the most exciting video you've ever seen produced by the FRL because pretty much nothing happens. After an hour, the cheesecloth was definitely discolored. Again, think about this though, from the ignition of that, the ignition viewpoint, there's no piloted ignition source. So we're still dealing with auto ignition of these fuels. So we have to get to that auto ignition temperature of that fuel in order to get it to catch on fire. Okay, so kind of thing to consider, they're baseboard heaters, they're a convective heater. Those aluminum fins are going to aid in convective heat transfer, but also help to keep our fuels away from the hottest part of the heater. Heating elements have been known to fail, and they can arc and spark and shoot out some molten material, which could be a potential ignition source. They have been known, some people who don't know any better might install these upside down. And so now that capillary tube is on the bottom and it's actually sensing the cold air coming in as opposed to the hot air going out the top. So that could be a potential issue, that it's now allowing it to run a little bit hotter. And this is kind of the last bullet point here, was the slide I skipped, but it's not allowed per code, but you can have instances where that thermostat is installed such that it only interrupts one hot leg of the circuit instead of both. And now, even though it's off, it's not calling for heat, you still have voltage present through the heating elements that could lead to a failure, even though it's turned off, if there happens to be a ground fault on the heating element. Okay, so typical failure modes, do we have thermal protection that's failed or bypassed? Does something come in contact with the heating element itself? Do we have some sort of high resistance connection? Is it installed incorrectly? So we're going to be looking for arc melting nearby or immediately inside. What fuels are available? Are there fuels inside or debris inside consistent with contact with a fuel? So that's kind of it. I mean, it's, baseboard heaters are I think they're fairly uncommon ignition sources. Okay, so last little bit, and I think it's kind of worth discussing, and we may have to hit it repeatedly if we continue to talk about various appliances, but spoliation's kind of is a hot topic, and this is the 921 definition. And really, I think everybody involved in fire investigation has the responsibility to preserve evidence. I don't think anybody would argue with that. The decision, or deciding what is evidence and what isn't, or what's important, kind of is dictated by who you are working for, who you're representing. So me as a public sector engineer, I might not be as worried about certain things compared to other folks that come along behind me, but I have to be cognizant of the fact that there are private entities coming behind me that might have an interest in certain products or appliances or devices. So we have to keep that in mind no matter what we're doing on a fire scene.
Yes, sir.
I'd like to have an argument, please.
Sir.
So that's the lighthearted banter, and usually kind of comes into play when I'm in front of a live audience. But when it comes to examining appliances, I would urge you to read this chapter 17, section 1711.1, and think about these three questions. What's the difference between destructive and intrusive? What training do you have? And do you have some sort of policy within your department or your company or your agency? So this section talks about, hey, if you're going to look at something, you might have to make some changes to that product in order to fully evaluate it. And so that might mean you're removing debris or making changes, and those changes in and of themselves don't change the evidentiary value of that device or that product or appliance. So they go so far as to describe, we're opening a cover, we're opening an outer case or enclosure, we're opening a door, we're removing a door, maybe we're cutting away or clearing off charred material or plastic or anything like that. That those things are obscuring our access to something important. So yes, they alter the device or the appliance product, widget X. But overall, if done carefully and thoughtfully and are documented, they don't change the overall evidentiary value of those items. So I typically, I'm trying to get ahead of myself here. So the big thing is, if you don't know kind of how a piece of equipment is constructed, don't let the first time you take something apart be on the actual evidentiary item. Maybe practice with an exemplar or get help and ask for assistance from somebody prior to doing anything. Because really what this section says is, if you're comfortable, or if you've got the training to look at something, but you're not comfortable taking it apart, don't touch it. If you are comfortable, but you haven't had the training, definitely don't touch it, because you're the most dangerous guy out there in the industry, just taking stuff apart willy-nilly. And if you've got training, you're comfortable going a little bit further and taking something apart, does your agency or your company have a policy that says you are allowed to do something? This is text that's been around for quite a few cycles now, in 921. So it's been around for a while and it hasn't really changed as far as I'm aware. But the reason I go through this is I do think that sometimes if we're going to opine that a space heater is an ignition source, particularly for the heater we just went through, that milk house heater, I could unscrew 8 screws, open up the 2 halves, identify all of the components that we just went through and said, hey, there's no evidence of failure. I might need to think of something else, or I might need to consider this less as a failure and more of a, did something get introduced, or is it too close to combustibles? And then you could take those same 8 screws, put it back together, and you haven't done anything to destroy that for anybody coming along behind you. Again, the key factor is doing it carefully, documenting it, and not, I like to say, taking a hammer to it and beating the crap out of it to get it open. If done thoughtfully and carefully, and for the right reasons, I think those types of examinations can be done by anybody in the public sector or the private sector. That's kind of my take on 921 and what it says. But yeah, I think that's kind of it in a nutshell. So yeah, that's kind of it. If you've got questions, let me skip to the end. Feel free to shoot me an email. Always happy to help. Contact your local ATF CFI if you want some assistance on a scene or want a piece of evidence looked at. We are all more than happy to help anybody.
Hey, Cam, great, buddy. Another great presentation. We appreciate you doing this and helping out DCARI and everybody else in the fire investigative community.
My pleasure.
If you know anything about DCARI, on our website under the test tab, we'll have a 10 to 15 question test available where you can get tested hours for your IWI, CFI, and any other continuing education that you may participate in. Any questions at all, just reach out to us. We do have a private Facebook page. That's DCARI, or Dane County Arson Response Initiative. And then also check out our website at www.dcariwi.org. Hey, thanks, Cam.
You bet. Thank you.